All right. Hey guys. So these are going to be my really quick notes on conservation of momentum. Um, and so let's begin. So after you guys make the new page in your composition book, what you'll want to do is go to that page and write down our investigative question, which is how do we apply momentum conservation to the calculations that we were doing in the simulation from yesterday. So let's go ahead and get that going. So first off, momentum conservation. What you guys should have seen yesterday was the following, which is that in all collisions, regardless of whether it was 100% elastic or it was 0% elastic or inelastic, then momentum should have been conserved in all cases. And so the way that you can write that equation wise is you can say that the total initial momentum is going to equal to the total final momentum. And this was something that was introduced to you with the simulation that you guys did. But you will have seen that I went ahead and wrote P tote. Tote stands for total. And then I, the I standing for initial. So P total initial is equal to P total final. So at this point, I would emphasize that you guys pause the video and write this in your notebook, and then we're going to jump to some examples in just a second. So pause right now. All right. And now we're going to move on. So let's do some examples. This example right here is the blob example. And so let's just go ahead and work through it. We're actually going to use the very same convention that we used for the simulation that you guys did the other day. And we're going to use something called an MVP chart. So let me go ahead and switch to my pen. And let's just go ahead and emphasize some things. So it says a 2 kilogram blob. So we'll go ahead and we'll underline that. Of putty is moving at 3 meters per second, and it slams into a 2 kilogram blob putty at rest. Okay. And so let's just go ahead and make sure that we understand this scenario. So we have a blob. So let's go ahead and draw blob A. And this is going to have a mass. Let's call it MA. And it's just kind of moving along at velocity VA. Okay. Next, what we're going to have is we're going to have another blob, a similar blob. And that's going to be MB. Okay. And this is going to have zero velocity. So we'll say VB is equal to 0 meters per second. And that's because I want to emphasize at rest, right? And so let's just go ahead and see what happens when we construct that diagram over here. So I want you to write this in your notes, but you're going to have 2 rows. You're going to have an A row and you're going to have a B row. And next, what you're going to do is you're going to write M as your first column. You're going to write V as your second column. You're going to write P as your third column. And very lastly, you're going to have your total momentum right here. Okay. And so go ahead and draw this table as I'm doing. Okay. And let's just go ahead and fill in the blanks. So for this first column, MA is going to be 2. And for our second column, the mass is also going to be 2. Now let's go ahead and do our velocity. Okay. So for our first blob, the first blob is coming in at 3 meters per second. So we'll go ahead and write 3 meters per second. But then our second blob was moving at 0 meters per second. And so it's going to have no momentum. So what I really like about these MVP charts is that you can literally just multiply across. So M times V, so 2 times 3 would equal to positive 6 as our first one. And then M times V, so 2 times 0 would be 0 as our second momentum. Okay, now just like we did in the simulation, we're going to go ahead and add those two. So 6 plus 0 would give us a total momentum of 6. Okay, and so it kind of goes without saying, but this was our initial momentum. So I'm going to write it so that now we can calculate what the final momentum is. So we're actually going to draw the same exact chart, but we're going to draw it backwards. So let's do P total final. Okay, and I really want to emphasize, right, that P total initial is going to equal to P total final, assuming that momentum is conserved, right? So this answer would also be 6. Now over here, we're going to fill it in backwards. So P, you could go ahead and fill in your table. Okay, we got V, and we got M. Okay, now I'm going to specifically not have 2 rows because you'll notice that in this problem, the blob, right, it went ahead and it slammed into the other blob. And so these two masses combined. So now that they're stuck together, it's going to be MA plus B. So we can already see that that would be 2 kilograms plus 2 kilograms. So that would be 4 kilograms over here. And since they're combined, they're going to have exactly the same momentum over here. And so how do we solve for this? Well, by definition, momentum, P, is equal to M times V, right? And so we could go ahead and divide the mass to the other side. Okay, and that would go ahead and do it for us. So let's go ahead and cancel out mass. And so our velocity will equal to P divided by M, which is 6 divided by 4, which simplifies to 3 halves. Okay. And so that's it. That's our velocity. It would come out as 3 halves meters per second. So, okay, let's take a look at the second part. So the second part says, all right, well, what if one of the blobs was 4 kilograms instead of 2 kilograms? So what would change? Well, I'm going to go ahead and change colors really quick, but hopefully this is pretty easy for you guys to kind of solve. So it says that the blob that's at rest is 4 kilograms. So we would go ahead and come over here and change that to 4. Right? But then 4 times 0 is still 0. So this total momentum stays exactly the same, right? Let's come over here. The only thing that changes would be the mass. So it'd be 2 plus 4, so it'd be 6 now. So let's go ahead and change that. Okay. And so if it's 6, well then if we do P divided by M, it would be 6 divided by 6, which is just equal to 1. So down here, we could say that the velocity is now equal to 1 meter per second. Okay. So hopefully that's pretty easy. I call this example, well, you're going to see 2 different examples. I call this example one where the 2 blobs are going to come together and become one mass. And the next example is going to be where they start as one mass and then they explode off of each other. And so in the 2 examples that I'm going to hold you guys responsible for knowing, I'm going to always have a scenario where they combine their masses together. So let me go ahead and clear the screen, and let's move on to the next slide. Okay. All right, so example number 2. We're going to go ahead and solve this using the exact same MVP chart. And I would highly recommend that you write this example into your notes as well. So let's go ahead and read this together. So it says, a 70-kilogram woman and her 35-kilogram son are standing at rest on an ice rink as shown. They push against each other for a time of 0.6 seconds, causing them to glide apart. The velocity of the woman immediately after they separate is 0.55 meters per second. Assume that during the push, friction is negligible, and so you don't have to worry about losing momentum or anything. So the question states, calculate the velocity of the sun after they push. Okay. So let me go ahead and get my pen. I'm going to use a different color since I wasn't wholly satisfied with using blue. And I'm going to go ahead and label the mom as MA. I'm going to label the sun as MB. And we're going to go ahead and actually solve the exact same MVP chart. So let's go ahead and do that. We'll have A up here, and we'll have B down here. We'll go ahead and we'll have the mass, we'll have the velocity, the momentum, and then we'll have the total momentum right here. And so we'll just, again, just solve exactly the same way. Okay. One thing that's going to be different, though, is that in this scenario, when they start, the parent and the kid are going to be one mass. So you'll see that it's 70 and 35. So 70 plus 35 is going to be 105. So let's go ahead and add that, 105. Now, before they push off of each other, they have zero velocity. And I hope that you guys can all kind of confirm that with me. They're not moving before they push off. So that makes our calculations really easy because if we follow MVP, M times V, 105 times 0, would give us 0 momentum, which means that the total momentum of the system is 0. Okay, so let's go ahead and do the reverse and see what happens when they push off of each other. So P total. Okay. So we have 0 again. Now, they're going to be separate since they're pushing off of each other. So let's go ahead and make 2 different rows. You'll notice that this is literally just the opposite of the previous example. And let's do V, and let's do M. Okay, so let's do the mom as the first row. So we have 70 kilograms first. And it says that the mom is going to push off with 0.55. So 0.55. Now, the parent, or the kid, I'm sorry, has a mass of 35. And it seems that we have some, information that's not complete. But luckily, we do have M and V, so we could really quickly calculate the momentum. So let me go ahead, pull out my calculator. And let's do that. So we got 70 times 0.55, and I get an answer of 38.5. So let's go ahead and do that. So positive 38.5. I apologize that that doesn't fit in the box, but hopefully you guys are able to read that. Okay, so it should become really clear, hopefully, that this momentum, momentum A, plus this momentum right here has to equal to this momentum, this total momentum. So 38.5 plus what number equals 0? And hopefully you guys are kind of sitting there thinking, well, that's super easy, right? It's going to be negative 38.5. And so if I know that it's negative 38.5, then that's the momentum. I can use the same convention. We have P divided by M, and that would equal to V. But I really want to stop and talk concepts for just a second. So let me switch kind of colors. And this is something that I emphasized in class as well. But you'll notice that the mass right here for the parent is 70. So let me go ahead and circle that. And the mass right here for the kid is 35, which is exactly half of the mass of the parent, right? Now, when they push off of each other, by Newton's third law, the forces have to be exactly the same, right? So if the force is the same, but the mass is different by exactly a half, well, then you would expect them to have literally a factor of 2 difference when it comes to the velocity, right? That's going to be the only way that this works out. Now, you could plug this into a calculator and do P divided by M, but always be on the lookout for these little conceptual kind of fixes that you can see. I know I saw it really quick, but if you don't see it, that's totally fine. If it has to be twice the velocity, right, then 0.55 times 2 would be 1.1. And if you plug this into your calculator, you're going to get a value of 1.1. Now, 35 times 1.1 does not equal to negative 38.5, so we are going to have to put a negative sign. But don't be too alarmed, right? That just means that the kid is just going in the opposite direction. Okay, so that's it with the notes. You guys are going to move forward into the online practice, and I'm going to be making a separate set of video instructions for that. Okay, please reach out to me if you have any questions, and I hope that this makes sense.